Power factor correction. Outline definition. Causes of low power factor correction. Advantages of power factor correction. Disadvantages of low power factor. Conclusion. Definition. Power factor, P.F, is a ratio between actual power to the apparent power. P.F equals actual power / apparent power, equals kW / KVAR. For a purely resistive load, the power factor is unity. Active and reactive power are designated by P and Q respectively. The average power in a circuit is called active power, and the power that supplies the stored energy in reactive elements is called reactive power. Power triangle. Causes of low power factor. A poor power factor can be the result of a significant phase difference between the voltage and current at the load terminals, or it can be due to a high harmonic content or distorted / discontinuous current waveform. Causes of low power factor. Poor load current phase angle is generally the result of an inductive load such as an induction motor powered transformer, lighting ballasts, welder or induction furnace, induction generators, windmill generators and high-intensity discharge lightings. A distorted current waveform can be the result of a nonlinear load like rectifier variable speed drive, switched mode power supply, discharge lighting or other electronic load. Power factor correction. Most loads on an electrical distribution system fall into one of three categories: resistive, inductive or capacitive. In most plant, the most common is likely to be inductive. Typical examples of this include transformers, fluorescent lighting and AC induction motors. Most inductive loads use a conductive coil winding to produce an electric magnetic field, allowing the motor to function. All inductive loads require two kinds of power to operate: active power, kW, to produce the motive force; reactive power, KVAR, to energize the magnetic field. The operating power from the distribution system is composed of both active, working, and reactive, non-working, elements. The active power does useful work in driving the motor, whereas the reactive power only provides the magnetic field. It is not usually necessary to reach unity, i.e. It is not usually necessary to reach unity, i.e. power factor 1, since most supply companies are happy with a PF of 0.95 to 0.98. By installing suitably sized switched capacitors into the circuit, the power factor is improved and the value becomes nearer to 1, thus minimizing wasted energy and improving the efficiency of a plant. Or power factor can be increased by synchronous motor or synchronous generators. Power factor correction methods: static Var Compensator (SVC), capacitor banks, synchronous condensers, static synchronous compensator STATCOM, static Var Compensator (SVC). The static Var Compensator is a thyristor-controlled, hence static, device which controls the flow of reactive power in a system by generating or absorbing reactive power. The SVC regulates voltage at its terminals by controlling the amount of reactive power injected into or absorbed from the power system. When system voltage is low, the SVC generates reactive power, SVC capacitive. When system voltage is high, it absorbs reactive power, SVC inductive. Control is achieved by a variation of the firing angle of the thyristors. It is prudent to keep reactive power flows to a minimum in order to allow the lines to carry more active power. Static Var Compensator. Capacitor Bank. In the electrical trade, the capacitor bank is used for power factor correction. A bank of capacitor is connected across the load. Since the capacitor takes leading reactive power, overall reactive power taken from the source decreases and system power factor improves. The capacitive reactance is used to offset the inductive reactance caused by inductive loads, motors. Motor loads can cause the power factor to drop to 0.8 or lower, and for this the customer is penalized by an extra service charge. The goal is to have a power factor level above 0.9, where there is no surcharge from the power supply authority. The cost of installing a capacitor bank is soon paid off from the absence of the surcharge. Capacitor Bank. Synchronous Condenser. A three-phase synchronous motor, when overexcited, works as a synchronous condenser or a capacitor. It gives dynamic power factor correction over a wide range of its excitation. When underexcited, it operates at a lagging PF and therefore absorbs reactive power from the bus. When overexcited, a synchronous motor works at a leading PF and therefore acts as a generator of reactive power and therefore behaves like a capacitor. Synchronous condenser. Static synchronous compensator, STATCOM. The static synchronous compensator, STATCOM, is a shunt device of the flexible AC transmission systems, FACS, family using power electronics to control power flow and improve transient stability on power grids. The STATCOM regulates voltage at its terminal by controlling the amount of reactive power injected into or absorbed from the power system. When system voltage is low, the STATCOM generates reactive power, STATCOM capacitive. The STATCOM basically performs the same function as static Var compensators but with some advantages like long-distance transmission systems, power substations and heavy industries where voltage stability is the primary concern. Static synchronous compensator STATCOM. Power factor measurement. Power factor can be measured by using power factor meter, which is well known in power industry. A direct reading power factor meter can be made with a moving coil meter of the electrodynamic type, carrying two perpendicular coils on the moving part of the instrument. The field of the instrument is energized by the circuit current flow. The two moving coils, A and B, are connected in parallel with the circuit load. One coil, R, will be connected through a resistor and the second coil, B, through an inductor, so that the current in coil B is delayed with respect to current in A. At unity power factor, the current in A is in phase with the circuit current, and coil A provides maximum torque, driving the instrument pointer toward the 1.0 mark on the scale. At zero power factor, the current in coil B is in phase with circuit current, and coil B provides torque to drive the pointer towards zero. At intermediate values of power factor, the torques provided by the two coils add and the pointer takes up intermediate positions. Power factor meter. Power factor measurement. Power factor can also be calculated by installing wattmeter along with the ammeter and voltmeter by using the power factor basic formula. Power factor equals actual power / apparent power. Power factor measurement. Advantages of power factor correction. Eliminate power factor penalties. Increase system capacity. Reduce line losses in distribution systems. Conserve energy. Improve voltage stability. Less total plant kVA for the same kW working power. Improved voltage regulation due to reduced line voltage drop. Reduction in size of transformers, cables and switchgear in new installations. Increase equipment life. Save on utility cost. Enhance equipment operation by improving voltage. Improve energy efficiency, power cost reduction. Utility companies in many areas include a penalty charge in the electrical rate for low power factor. The installation of power factor capacitors on the user's electrical distribution system eliminates the necessity of paying premium rates to the utility company for poor power factor. System capacity increase. By adding capacitors to the system, the power factor is improved and the kW capacity of the system is increased. For example, a 1000 kVA transformer with a 70% power factor provides 700 kW of power to the main bus. With the installation of capacitors so that the power factor is improved, say, to 90%, the kW capacity of the system is increased to 900 kW. When a system power factor is improved, the amount of reactive current flowing is lower, thus reducing transformer and distribution circuit loads. Disadvantages of low power factor. Increases heating losses in the transformers and distribution equipments. Reduce plant life. Unstabilized voltage levels. Increase power losses. Upgrade costly equipments. Decrease energy efficiency. Increase electricity costs by paying power factor surcharges. Conclusion. By observing all aspects of the power factor, it is clear that power factor is the most significant part for the utility of the company as well as for the consumer. Company get rid of the power losses while the consumer free from low power factor penalty charges. By installing suitably sized power capacitors into the circuit, the power factor is improved and the value becomes nearer to 1, thus minimizing line losses and improving the efficiency of a plant.